So, um, as I said, if you guys feel like, even 10 minutes from now, if you feel like you want to move over to the right side of the classroom somewhere, just go ahead and do it. I don't mind. They're going to try to replace that after classes today, but can't do it right now. Office hours. Let me just reinforce to you the basic theory is that I have office hours. Actually, that's 10:30 a.m. to noon. That should say 11 a.m. to 1 p.m. on Wednesdays. Darian Fry, the TA for the morning class, she has office hours from 1 to 2 p.m. This is what Darian looks like. And that's the atrium where she works, because she doesn't get to use the room that we like to use for office hours is occupied during that time. So, but she'll be out in those big tables and stuff out in the atrium of the physics department. And she's really smart, and she's really friendly, and so you can really learn a lot from Miss Darian. And of course, yesterday we had a really good session in office hours. Morgan, where are you? Morgan. Morgan is not here. She was at office hours yesterday. A bunch of other students, so it was good. All right, let's do a little recap. Last time we talked about the law of universal gravitation developed by Sir Isaac Newton. I want to give you a sketch here, a diagram of the Earth-Moon system, which is governed by Sir Isaac Newton's theory of universal gravitation. And this diagram, I don't really know how you can do it, but I made a diagram here of the Earth-Moon system. The Earth is up in the upper left corner. The moon is this little teeny dot down here in the lower right corner above the blue banner. And here's the distance r. So the theory of universal gravitation is that gravitation is universal. It's an interaction between any two objects that have mass, m1 and m2, no matter what they are. And for the Earth-Moon system, so you are actually experiencing a gravitational interaction with the moon at this very minute. But the Earth is so much closer to you. It's the r from you to the center of the Earth is so much smaller than the r from you out to the moon that the main thing that you notice is the Earth's interaction with you. But does anybody know a visible gravitational interaction that can be observed on this planet because of the gravitational interaction with the moon? Yes. Tides. Tides in the oceans. Very significant in many places. So you can't really feel it right now because you're not as tall or as wide as an ocean. But the oceans, yeah, they're big enough to feel the interaction of the moon and rearrange themselves in the way that we now call tides. But in the Earth-Moon system, these are the true proportions. Here's the Earth, here's the moon down here. And in this diagram, the diameter of each is proportional in the true proportion. Also, the distance is in proportion to the sizes of both. So I think it's like every 1,000 kilometers is 4 pixels, I think, in this thing, something like, or 4.5 pixels for every 1,000 kilometers, I think it is, in this scale. So I don't know if you can draw a picture of it, but that's actually the true scale of Earth and Moon. So if you were in a spaceship or a rocket or something, or like you could teleport out into space, toward the North Star, so above the orbital plane of the solar system, so above the North Pole of the Earth, and then look back down at the Earth-Moon system, it would look about like in those proportions. And if you think about it, it's phenomenal how far the moon is away. And the moon looks really big. We can see it right now I saw it on the way to classes this morning. I got here at about 7:30, and some of you guys I know are not even out of bed at 7:30, but I was already here at 7:30, and I looked up, half moon, almost straight overhead. Last weekend was the full moon, and now we're at half moon, and at sunrise, when the sun rises, the half moon is overhead. And also, you know what today is? First day of fall, first day of autumn. So on the first day of autumn, the sun rises directly in the east. And did you, raise your hand if you were driving up University this morning, or about 7:30, and you were like getting blinded by the sunlight. Slackers! Nobody was up at 7. Okay, one guy. Okay. Oh, okay. Anyways, I love it because in the United States and a lot of places, roads are frequently oriented east and west, north and south, and so on 2 days a year, the sunset tonight is going to be the other end of University, and the sunrise is, you see at this end of University. It's kind of cool. Anyway, so this is the true proportions of the Earth-Moon system. And when you look at, like, if you go to a fifth grade science book and they're talking about the solar system and all that stuff, they don't use these proportions at all because they can't. They can't. Little kids are, what? I can't see it. So they gotta exaggerate the sizes of the Earth and the Moon. They may keep them the same size ratio, but not the true distance apart, given that ratio. So it's, but this is a true. Here's another one. If you, and this for those of you that are ed majors, secondary or elementary or early childhood, if you had one of those standard classroom globes of the Earth, about a foot in diameter, if that were the Earth, then the Moon would be a tennis ball about 28 feet away. So from me, over to, let's see, from me, yo with the baseball hat. Yeah, you. Yeah, stand up. Okay, so from me, now what's your first name? Cameron. So from me over to Cameron, that's about 30 feet. 20. So globe of the Earth here, and Cameron's holding a tennis ball. That's about the rough proportion. Yeah. Okay. Thanks, Cameron. Yeah. So that. Another thing we studied last time, the concept of momentum, around page 45, and so forth. This is the equation that we talked about a lot, the impulse equation. Let me push it over here to the left a little bit. F delta t, that's the impulse. That's by definition the impulse. Force times time, or force times interaction time. And then the effect of that force acting over time, hi Morgan, is to change the momentum. And so when you're working with this, something that we were talking about in office hours yesterday is that there's a couple different versions of the impulse formula that you may like to keep handy, depending on, what kind of problem you're working on. P is equal to mv. So if you have delta P, you have delta of the quantity mv. Now the guys down in Houston that work for NASA planning space flight, satellite orbits and so forth, those rockets lose mass as they accelerate up into the atmosphere and out to orbit. And so they have to use this version of Newton's second law because mass is changing. So they have to have they have to measure the change of both of those quantities. But for us, we're going to be mostly working with baseballs and atoms and stuff like that. So for us, the mass is fixed, and the only thing that changes is the velocity. All right. So F delta T is, for most of the time for us, well, for all the time, is going to be m delta V. Now, delta V, by definition, is V2 minus V1. Or sometimes you can write it VF minus VI, V final minus V initial. You know, whichever way you like to account for it. It's always V earlier, it's V later minus V earlier. Later, all deltas are later minus earlier if it's a dynamical system usually. Okay, and as I also mentioned, and which we struggled to do on the homework last night, was the stopping time problem. Usually it's easiest to use impulse. You know, you can use 1/2 AT squared, figure out forces and all that stuff, but usually the impulse formula is easier if you're trying to figure out delta T. And by the way, let me just apologize to you for the malfunction of homework problem 3 in homework 6. And I haven't figured out a way to avoid that, but what happens is in Canvas, when I transfer a really good formula-based problem like number 3, the baseball in space problem, I transfer a formula-based problem that works from one test bank to another test bank in web courses. It screws it up sometimes and changes it into a fill in the blank. You know, it was looking for text in there, so a lot of you guys had it, and it wasn't working right because it was looking for, it wasn't even looking for a number. So I fixed that, and I don't know why web courses does that, but it does seem to do that a lot. So anyways, that's what was happening. I fixed it. I don't know, maybe some of you guys mentioned it. Ashley, are you, or somebody mentioned, was it you? Was it you that mentioned it? So, okay, I heard you guys talking over there. Anyways, we fixed it, and I gave everybody an extra 2 attempts, which, you know, sometimes I have to do that. So, anyways, on this topic, when I say that it's usually easiest to use the impulse formula, for instance, this one, if you think about it, a lot of times, if you know or can figure out 4 of the 5 items in this, you know, there's 5 items here. There's F, there's delta T, there's mass M, and there's V2, and there's V1. And if you can figure out, like, for instance, these 4, the force, the mass, V2 and V1, or if it's in the problem, you know, then you can figure out the 5th item, the stopping time in this case. Right? So that's a strategy, and Morgan and Kayla and Malik and a bunch of guys were in there yesterday in office hours, and we just crushed this thing. We worked on it really hard. So, but I want to try some more impulse calculations with you right now. So get your clicker out. Also, get your calculator out and just have it handy, because we're going to need the calculator today. And by the way, Miss Caroline up here my trusty TA is going to give out exam printouts. If you didn't get yours on Tuesday, we've got them. And those of you that had blanks and stuff, we got those sorted out too. So if you don't have your printout, you can come up and get it after. We'll just probably dismiss early today. You can come up and get your printout. Yes, I heard a student over here go, dismiss early today. Yes. Did you go like this too? Yo, did you go like this? You got it? I mean, that's what that's what I always do. Anyways. All right. Question 1. You observe a large blob. Your grandma made some green jello with little, fruit cocktail in it. Oh, who has a grandma that makes that every 5 minutes? I don't know. Nobody's admitting to it. Anyway, how much impulse does the Klingon's tractor beam deliver in 2 seconds? Maria, you don't have SI today, right? Okay. I was trying to get the homework ready, but it's not quite ready, so. But if you don't have SI today, I guess it's not a big disaster. Because I like to try to get it ready for you. Yeah. "15 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Can you guys see okay over here? Move over to the other side then if you want. It's perfectly fine. You can disrupt class. I won't. No, you can move if you want. Anybody can move. You guys over there. All right, let's see what you guys got here. Ding. Oh, just like the morning class. You guys are gonna be mad. See this? There's a little bit of confusion. Not everybody agreed on the answer here. This is the answer. And hey, you guys, impulse. I kind of gave you a hint a few minutes ago. Impulse, F delta T. Ding, 12 times 2, 24. And the units of impulse are the units of momentum. Kilogram meter per second. So the next problem, and this one too, I hope you wrote this one down. Write down this one. Wait, can you go back really quick? Nope, I can't. Actually, okay, we won't dismiss early if I go back. Okay. Ain't I mean? Now you can look it up on YouTube. Unless you have a question. Do you have a question? Okay. All right, so here's your next question. Jot this one down too. And this is a stopping time question. And it's usually a good practice to either take a photograph with your iPad or copy it down in your notes. That's good. That's good. Copy it down in your notes, and then if you get this wrong, 20 seconds. No, I'll give you a little more time. Yeah, copy, just jot down the specs, and then you can double check it if you have to. 20 seconds. Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Let's see what you guys have got. Oh. We have no explaining to do. Most of you got it right. 1.6 seconds. But in case you didn't get it right, let's just go through the calculation. Here's the given information. Stopping time problem, and actually this is a little bit heavy. A true basketball from the NBA is a little bit less than this, I think. Anyways, for the mythological 0.800 kilogram basketball, 22 meters per second, using the impulse formula, first thing you got to do is get the momentum state figured out. Here's your delta. Delta P, 17.6 kilogram meters per second. And then your stopping force is 11 newtons. That's also in the problem. So to get delta T by itself, you then divide by 11. And so in this one, of the three quantities, F, delta T, and delta P, you have two. So you can get the third one, delta T. And in this case, it works out to 1.6. So if you want to quickly jot that down, you're good. All right. And Brian, as I've mentioned before, one of the things that you want to do as you go through lecture notes is think, and also use the lecture notes as your study guide. And this one is a good problem to have in your own personal study guide. And last semester, or I should say spring semester, I had some students that ripped me apart on my student evaluations because I would occasionally in class refer to a student by name. Like I just referred to Brian, and some of you, I know your names already, and I like to learn names, and I try to practice them by, if I look at a student, if I happen to look in his direction and I remember his name, then I say it. And if I don't remember your name, I'm going to try to remember your names. And I have gotten hundreds of students' names memorized before in a semester. So anyways, I do it because I like remembering names, that's all. Everybody's got one, and I like remembering them. Next topic, collisions. Now this is going to be an application of the impulse concept and the impulse formula, F net times delta T equals delta P, change in momentum. But in the situations that we're going to consider the two interacting objects as an enclosed system with no net external forces. Excuse me. Whoa. Ooh, that's in the podcast. I just burped into the microphone. Good going, Dr. B. Mike's monster. Anyways. So we're going to talk about boxcars out in the freight yard. And there's an example at the end of chapter 4 that you can look at, and in addition to what we're going to do now. So it's good backup. So look around page 47. And then the example, a long, thoroughly worked out example, is in the back end of the chapter, back end of chapter 4. So when I say that the net external force is 0, what that means is that, for instance, downward gravity of each boxcar is balanced by upward rigidity from the railroad track, and that there's no friction. So it's a mythological frictionless railroad, okay? But the boxcars are going to interact. They're going to, hook together. They latch together as they, slam into each other. That's how it works if you're ever out in a freight yard. And you know what I did one time when I was out in Montana? I hitched a ride on it like a hobo on a freight train. And I didn't like it. It was too fast. It was nice, though. I mean, I hung around all day in this freight yard in Laurel, Montana, and to get on the Burlington Northern. And we got chased by the cops a couple times. And then we came back, and it took us all day. And by the end of the day, I was sick of riding on the train, so I got off the first place it stopped, which is about 25 miles down the road, which I could have walked if I had walked instead of waited around for that train. Anyways, so boxcars. And that whole day I spent looking at boxcars in that big freight yard in Laurel, Montana. And they interact with each other. So when they hook together and lock, that's what they do in the freight yard. They reassign boxcars to different strings of boxcars. There are interaction forces. So there's going to be delta V between the boxcars, but not because of a force other than third law forces of one boxcar on another. Now let's get down to the specs of that. All right, here's our example that we're going to work out. We're going to say, all right, in this freight yard in Montana, we've got 3 boxcars already hooked together, and they're sitting there parked on the side on the siding, and they're at rest. And then we've got boxcar number 1 moving at 4.4 meters per second to the right. And I've given it a big, thick V1 arrow. All right. And he's going to interact with those other 3. He's going to latch on. Okay. And if you think about it, number 1 is going to bash into the string of 3. And so he's going to effectively push on the string of 3 boxcars. But by Newton's third law, the 3 boxcars are going to push back on number 1. And those interaction forces are going to achieve some delta V. And after the interaction, they all move off together at some new speed. All right? So they're now latched together, and the effective mass is now 4 times the mass of one boxcar, because you got 4 boxcars. And they're rigidly connected together, and so they move off as one unit. But the question is, how fast are they going to go? I mean, is it going to be the same speed? Is it going to be slower? Is it going to be faster? Now, what actually is what's the new velocity? V subscript nu. And so that's what we're going to try to figure out in this problem. And let's keep going. Here's some boxcars. Now, we're going to assume, just for conversation, that each boxcar is identical. Don't have to, but let's assume it's identical just for conversation purposes. 35,000 kilograms. That's 35 metric tons each. And as we've already stated, the initial state is V1 equals 4.4 meters for the boxcar number 1, and that for the group of 3, 0.0 meters per second. They're at rest. All right? Now, the interaction forces occur when number 1 bashes into the string of 3. Now, I want you to think about this for a second. Number 1 effectively has an interaction force over a time of interaction, delta t, like 0.1 second or something. So it has an interaction force to the right. It's pushing the string of 3 to the right. So the string of 3 is going to get a delta V to the right. Right? So they're going to start moving. All right? Let me repeat that. Boxcar 1 has an interaction force to the right for a certain amount of time, like a tenth of a second. So it's going to give delta V to the right to the 3 boxcars that were at rest. Now, third law says boxcar set of 3 gives an equal size force to the left. And it's going to act on boxcar number 1. So boxcar number 1 is getting pushed this way. And what effect is that going to have? It's going to slow him down. Because he's moving to the right. He's getting a pushback for just a split second to the left. Right? So he's going to slow down for that split second of interaction. Right? So V nu is going to be somewhere between 4.4 and 0. Okay, so And hopefully that appeals to your common sense. You know, it's not going to be going faster, and it's not going to be zero. It's not going to stop. It's going to be somewhere in between there. All right, let's figure it out, what it is. And we'll do it by analyzing the momentum. Now, the momentum in the initial state, P subscript I, is this quantity here, 35,000 kilograms, 35 metric tons for boxcar 1, times its velocity, 4.4 meters per second, positive number, so it's going to the right. And now these 3 0, I have plus 0, plus 0, plus 0. Now normally you don't have to add those in on an equation. But I've added them in to emphasize to you that those 3 other boxcars, they don't add any momentum because they're at rest. All right, now normally I don't write those zeros in, but I'm writing them in here just so you can see, just for bookkeeping purposes, you know, the sum of all 4 momenta. And that's the total momentum, the total initial momentum, P subscript I. All right, now you can calculate that and verify me on your calculator. 35,000 times 4.4, believe that works out to 154,000. Anybody verify me on that? Yeah, okay. Okay, so 154,000 kilogram meters per second is the units of momentum, a mass times a velocity. Now, there's no external forces. No unbalanced external forces. So F net is 0. But because that is true, the initial momentum and the final momentum have to be the same size. So P subscript F also has to be 154,000 kilogram meters per second. To the right. Right, so there's that. Now that, my wonderful students, is known as conservation of momentum. Conservation of momentum. If there are no net external forces, the sum of all the initial momentum is equal to the sum of all the final momentum. Now they may be redistributed, but when you add them all up as vectors, you know, with pluses and minuses if you're going left and right, east and west, then you should get the same number afterwards. Okay? Now, this equation, P subscript F equals 154,000 kilogram meters per second. Put a star next to that. The reason for that is conservation of momentum. All right? We can write that equation down because of conservation of momentum. Now, I'm going to extend that equation. One extension to it is just the definition of momentum, P equals mv. That's also true. We still have an mv in there. But now, the mass of this 4 kilogram object, 4 boxcar sized object, it's got a bigger mass, 4 times 35,000. That's 140,000 kilograms. So to us, it looks like 4 boxcars. But really, the momentum is as if it were one big boxcar of 140,000 kilograms, 140 metric tons. You know, well, the math works out that way. Because they're latched together rigidly, and so they all go off as one unit. So the mass of the new unit, 140,000 kilograms, times my new velocity, which we're trying to figure out. Can you see how to get V subscript new? Raise your hand if you can see it. Can you see it? Who can see it? How do you get V sub? Come on, you guys over there on the right. Are you thinking? How do you get V? Look at that. Can you see how to get V subscript new? Yeah, you got to divide. Let's divide now. All right, so that's definition of momentum. And here's your division. All right, and that gets us V new by itself. So 154,000 kilogram meters per second by conservation And then new mass, 140,000 kilograms. Anybody verify me 100? No, not 100. 1.1? Anybody verify me? Good. Okay. And yeah, just bring your calculators with you. And I believe you're going to have some of this for homework tonight, for homework 7. Question? Isaiah, right. Yeah, 140,000 in the numerator here and over here. See this quantity here? This is MV, all right? Definition of momentum. But the M is the mass of all 4 hooked together. So 35 times 4, 140,000. Okay, 35,000 times 4. All right, so that's where that comes from. Another question. Yes?
Is it just a coincidence that since the 3 are going at 0 and then the other one's going at 4.4, that is divided by all 4, it would be 1.1? Is that just a coincidence?
I don't believe in coincidences. I believe in, well, I don't believe in F equals MA. I mean, I just, that's like saying, it's what the numbers tell you. And it's not a coincidence.
When I look at an equation like this, I go, okay, so before I really get into the equation, what's like the most simplest way you can look at it? And I think, all right, 4.4, the other one's 0, divided by 4. And I was like, oh, 1.1. But then you did the whole equation and it ended up being 1.1. So I just...
Well, it's an interesting theory. It's not a coincidence. It is what the numbers say. Your instinct, your eyes, you just saw a pattern. The denominator here is 4 times m, or 4 times m1, because they're all identical masses. So good eyes, you saw the pattern. Let's just write it out. A couple comments first. The skateboarder example in the textbook at the beginning of chapter 4 is pretty good. I didn't work out the momenta, but you can, and they will balance before and after. Matter of fact, before the interaction, it's 0. So after the interaction, those skateboarders, and the nice thing about that one is the momenta are different sizes. No, I take that back. The momenta are the same sizes, but the velocities are not, and the masses are not, and they're opposite directions. Okay, so it's a little bit different than a collision. This is one thing banging into another, and then they all go off in one direction. The skateboarders were at rest, and then they both go off in different directions. But momentum still holds. And here's the principle. The total momentum of a group of interacting objects remains the same in the absence of external forces. And it really should be unbalanced external forces. So go ahead and add that into your notes, unbalanced external forces. And hey, you guys, if you do have external forces acting, unbalanced external forces, you can handle that. You just got to use F equals MA. So it's a little bit different approach. But yeah, for an interacting, any kind of a collision, yeah, most of the time we model that as a conservation, a momentum conserving system, a momentum conserving interaction. And we do the same thing in this example as we do with molecules and atoms. If you're over in that big atom smasher in Geneva, Switzerland, where they're trying to measure the Higgs boson and all that, which I know a lot about, that atom smasher, they analyze conservation of momentum at the watt. Actually, their computers do it. Somebody programs the computers to analyze conservation of momentum, among other things. And they do it for millions of collisions, and then they sift through all the collisions, and hopefully they measure the Higgs boson and all that it means. for our model of the universe. All right, we did a boxcar example, step by step. Let's see. Young lady in the back, you were asking me about the pattern. What's your first name? Stephanie? Okay, Stephanie. Here we go. Now this one, well, it's Stephanie and everybody else. Here we go. All right, now let me select numeric. All right, here's your problem. 4 boxcars, same 4 boxcars, different day, different speed. And jot this down. Jot the specs down for this one too. Because if you get it wrong, you can go back and double check as you study. Because I'll give you the answer in just a minute. And I'm not going to turn up the lights since the displays are kind of dim. But definitely work with your neighbor. I see people pointing at the screen and pointing at their notes. That's good. Talk to your neighbor. Make friends with your neighbor first, then talk to them and discuss. Just discuss Stephanie's concept. It's good. I mean, it's great. But it's not a coincidence. But does it apply here? Work out the numbers and see what you can see. Once you get in this scientific system, you can make predictions. It's interesting. I have this copy of USA Today from last Friday. And I was going to read it over the weekend because I like to read the football predictions and stuff and the crossword puzzle and whatnot. But I didn't get to it. So what I'm going to do this weekend is tomorrow on my day off, I'm going to study this and see how well they predicted what actually happened in college football and NFL football. This prediction is tough. Hard to do. But what we're predicting scientifically, the prediction of the future state of this boxcar system is much easier. 45 seconds. Oh, Caroline, thanks for getting me that monster. Whew, man. We just got back from summer vacation. Already I'm ready for another vacation. Gosh. Yeah, it is the weekend for me. As soon as we're done here, and all those other people in here that raised their hands, dismiss early for the weekend. Yes. Okay, 10 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Let's see what you guys got here. Let's see. Wow. I see a lot of geniuses here. 1.6. That's the correct answer. Okay. But don't go with, still work out the numbers because you never know, Doctor. Yeah, that's good. Now, next topic, energy. Let's keep going. And this is starting around page 49. Now, we've got a lot to work on here. Stephanie.
Are we ever going to have an example on the test where, like, it's a different weight or it has the other objects have different speeds? Are we going to know how to work with it by then? Not because I want to do, like...
That's a great idea for a brain burner on midterm exam 2. Okay, Stephanie. I'll even name it after you.
No, I'm
No.
know how to do it when it's
Yeah, if you can hack the boxcar, and if you can remember positive and negative for rightward and leftward, you can hack the interaction of two boxcars coming from opposite directions and what's going to happen.
My
So
other question is, when you have different speeds, I know how plus 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 or whatever it is, do you add that to the existing ones before you multiply it by the mass, or do you do that after you've already multiplied it?
the initial momentum state is comprised of the momenta of each object. So you just got to
All
calculate.
that's added and then you multiply by it.
And then you say, all right, that's going to be the net or the total momentum after the interaction. And then you split it up again if you have to. So, energy. Now, I forgot to animate this, so we'll just go through this outline here about momentum and energy in four-dimensional context, four-dimensional space-time, item by item. Now, we'll think about, as Galileo did, the simplest accelerated system where the speed and the trajectory are changing slightly, and that's free fall, a baseball. Now, he didn't have any baseballs, but we're going to use a baseball. And when you drop a baseball, if you divide up the path second by second, so like with a strobe camera, strobe photo, you take one flash of the strobe every 1/10 of a second, or every 100th of a second, or every half of a second, or whatever you set the strobe to, you'll get the same increment of downward speed for every flash of the strobe. So if your strobe flashes once per second, you'll see an additional 9.8 meters per second negative for each new flash. Similarly, you'll see delta P increase, or I should say decrease, more and more negative, negative 1.42 kilogram meters per second for every second of free fall. And that's for a regulation size baseball, 145 grams. Okay, so number 1A, capital A, is like a stroboscopic set of photos. And if you think about it, if you look at something in free fall, a strobe photo of it, the first two images of the baseball falling are pretty close together. But then for later flashes, there's quite a distance between flashes because it's going faster. Faster and faster. Delta V is increasing. So, side note, 1A3, delta Y is not uniform. Delta V is, delta P is, but not delta Y. You're getting bigger and bigger delta Y's. So those don't fit the pattern, the distances. But equal increments of time, you get equal delta V's, equal delta P's. All right. 1B, every meter of drop distance. So now if you think about the baseball falling and you record it like in the homework, every meter of free fall, then you get downward speed. V squared is the thing that increments the same each time. And because there's a concept called kinetic energy, 1/2 mv squared, for which you see the formula here, Ke equals 1/2 mv squared, the energy of motion, which you get by doing a bunch of calculus. So calculus 2, and which we're not going to go through, but the result of it is, yeah, on any trajectory, the energy of motion, 1/2 mv squared, does get apportioned in equal increments of, in this case, downward motion. So this increment of kinetic energy is also known as the work, W-O-R-K. And we're going to use capital W for the symbol of work. We'll get to the formula for it in a minute. But I want to emphasize to you, raise your hand if you're in business or if you've taken a business major or you've taken a class in business. Okay, that's a bunch of you. Now, if you're a business major or you've taken a class in business, you know that there's different accounting schemes. Now, my wife is an accountant, and I don't really understand what she does. But I understand that there's net receivables and payable accountables or accounts payable and accounts receivable and all that stuff. Does anybody here understand what that is? Accounts payable, accounts receivable? Well, you will by the time you're done. Oh, Brian, you know. Okay, good. At least one person knows. Anyways, different ways of accounting for the money that comes in and out of a business. The same thing here. Different ways of accounting the dynamics of a falling baseball. Second by second, okay, we know how to do that. Meter by meter, yeah, we know how to do that if we use kinetic energy. And kinetic energy is the quantity that's going to correspond in a four-dimensional situation or four-dimensional context. It's going to partner up with momentum. Now, let's talk about momentum for a minute. And to do that, you have to talk about the three spatial dimensions. Okay, now if you think about the lectern up here in the front, okay, the lectern is arranged left to right. So the x-axis, you can think of as the left and right dimension up here in the front. Now, floor to ceiling is the y-axis, okay, according to this diagram. And then the z-axis, the third spatial dimension, you can think of as up the aisle or down the aisle, okay, or towards the back of the room or towards the front of the room. Okay, that's the z-axis. And because those are the spatial dimensions, and because you can have velocity across either of those dimensions, momentum also has components in the x direction, the y direction, and the z direction. So the momentum, P equals mv, vector P equals mass times vector v, velocity. That can be broken down into a little bit of x momentum, P subscript x, you know, either left or right, and a little bit of y momentum, maybe, you know, some upward or some downward momentum, and a little bit of z momentum towards the front of the room or towards the back of the room, you know, P subscript z. So, and here's something else I want you to make a note of. The XYZ coordinates, those are geometric. PX, PY, PZ, those are dynamic. Those are dynamical. Right? One is geometric, one is dynamical. Right? Now, in four-dimensional space-time, we have the three spatial dimensions, and the fourth dimension is time, or as we would say it in precise terminology, the temporal dimension. Right? And I'm sure many of you have heard the fourth dimension. Time is the fourth dimension. Right? Now, the dynamical quantities that encode interaction are momentum, which can have coordinates in the x direction, the y direction, and the z direction. So it's spatial. The momentum is a spatial vector. But then what corresponds to the temporal dimension? So four-dimensional space-time, geometry-wise, what about four-dimensional dynamics? Well, three of the dimensions dynamically are taken up by the momentum vector. The fourth dimension is encoded in the energy of a system. For instance, this famous equation, E equals mc squared. Yep. That's the temporal part of the dynamical description of any object in the universe, really. Kinetic energy is also part of the temporal or the four-dimensional description of the dynamical state of any object. And there's many other forms of energy, and we'll be talking about several of them this semester. When we get to talk about atoms, in specifically about atoms and molecules, the periodic table, towards the end of the semester, we're going to be talking about electrical forms of energy. You know, volts and stuff. Let's keep going. This dynamical quantity, energy, it should be somehow analogous to the impulse concept. So the impulse was F delta T equals delta P. So you might think to yourself, okay, delta KE, KE is the dynamical quantity. It should be, like F net times a chunk of the path, delta S. Delta S is a generic description for a small segment of the path, whether it's along the x-axis, left and right, or the y-axis, up and down, or the z-axis, to and fro, or some combination, or a curved path that curves through all three dimensions. Take the path and take a little chunk of it, a little slip of it. It's going to have a direction and a length, and that's delta S. Now the problem with this, here's your velocity, right? So to go ahead and draw a graph or a path, some generic, give it a little curve. And I picked a point up here on the first curve, and I drew in a velocity vector. The problem is that the net force on an object might be perpendicular to the path, and that is a problem, or that is difficult for us, because the pattern that you looked at in homework, the pattern in V squared, which hopefully you saw, the pattern in V squared is not about a direction, it's about speed. And so perpendicular forces, like for instance, if this is your path and this is the net force acting, if this is the net force acting on your path or acting on your object as it follows this velocity through path G, you got a problem. That's like a Maserati accelerating through the curves. So if you're in a car and you're going through the curves and you don't have cruise control on, you might be speeding up. And if you are, you might have a force on your car like this. A little bit in the direction of the velocity and a little bit into the turn. Because you're turning. Okay? And that's a problem. Now, let's take a look at this net force vector. We're going to break it apart into two components. Now, they're not going to be x and y, in this diagram anyways. One component is going to be parallel to the path, and one component is going to be perpendicular to the path. So here we go. Let's take a look at this. So I've got my path up here. I want F parallel. And the way to do that, first I'm just copying my net force down to the bottom here where I have some room to sketch. Now, I draw a second arrow, F parallel, that's at the same tilt angle as the velocity up here. See that red velocity arrow where my cursor is? Okay, and that's the same tilt angle as F parallel. And it forms a right triangle with F perpendicular. That's the other component. And that's the component F perpendicular. It's perpendicular to the velocity. Okay, F parallel is parallel to the velocity. F perpendicular is perpendicular to the velocity. And they form a right triangle. Here's the right triangle, right? Eyeball that. Look at that. There it is. There's the right triangle. So F net is the hypotenuse of this triangle. Whoops. Let me go through here again. I just I hit the wrong button here. Do-do-do-do-do. All right. Copy. F parallel. F perpendicular. Right triangle. All right. Here it is again. F parallel. Here's the right triangle. Okay, and now I'm going to take that F parallel. Hopefully you believe in the right triangle. You believe in F parallel. Now I'm going to copy it and move it back up here. All right, so they're parallel. So there's some newtons parallel. So here's one way you can express it in words. Any net force like this has a few newtons parallel to the velocity. And then there's going to be some newtons perpendicular to the velocity, F perpendicular. And F parallel is the component of the net force that changes the speed. Right? Because if F parallel is in the same direction as the velocity, then you're going to get more speed. And that's what changes V, and in turn, V squared reflects that same change. So let me ask you another question on the clicker. See if I can get this. And hopefully, I will not catch you napping the way I did the morning students, but you never know. It's possible to catch students napping at any time. That's why I get up so early in the morning. Gonna stay one step ahead of you guys. Perpendicular, F perpendicular. What does that do for the motion? "30 seconds. Remember to think. "10 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. All right, let's see what you guys voted for. We got some splaining to do here. All right. Now, some of you voted for A and some of you voted for C. Most of you voted, majority voted for C. C is correct. Remember, if you're perpendicular to the velocity, you're not speeding it up because you don't have any newtons in the direction of the velocity. And you're not slowing it down either because you don't have any newtons against the velocity. If you're perfectly perpendicular, yeah, all you do is change the direction. Make a note of that. Now, let's go back to the analogy with impulse. Delta P equals F net times delta T. For this four-dimensional analog, it's delta KE equals F parallel times delta S. Whatever the path is, F parallel to that path, yep, F parallel times delta S is equal to the change in the temporal or fourth dimension of the dynamical description of that object. Delta KE is known as the work done by F parallel. Now, let me ask you, what direction is the weight force? It's downward, all right? So if you're on a Y trajectory, your delta S would be a delta Y. Okay, delta S is generic, but if you know the trajectory, straight down, baseball path, delta Y. All right? So the work done, so go ahead and write this down. It's not on the notes, but you can write it down. the work is equal to mg times delta y for the work done by gravity on an object of mass m. Work W equals mg delta y. If that's the trajectory that you're on. Another thing that gets apportioned equally is something called gravitational potential energy. Gravitational potential energy is the opposite of the work done by gravity. It's minus mg delta y, and in this one you have to use negative 9.8 meters per second squared for the value of g. GPE increases when delta y is positive. So delta y is positive, g is negative, and there's a minus sign, so there's two minus signs in the GPE formula. So minus times minus is positive, right? So GPE increases on the way up. It decreases on the way down. But let me ask you this. Item 1, item 1, part C, what is it that increases when you lose altitude? What increases? What do you say? You're not saying anything? I can hear your mouth moving. Okay. What increases? Kinetic energy. I heard some. Did you say that? Somebody said it. Yeah, kinetic. Sweet. Yeah, kinetic energy. So 1C, kinetic energy increases when you lose altitude. And that, Stephanie, is not a coincidence either. So for every kilogram of mass of the object, and for every meter of altitude of the object, the GPE is defined. Right? The gravitational potential energy is defined. And we call it the energy of position. There's a load of calculus behind that. But here's a table of concepts that, we're going to expand on number 1 here. So when you go to the top of the plateau here, that means y is increasing. You're going to a bigger y value. So say 0 is at the bottom of the mountain. At the top of the mountain, top of the plateau, you're at 1,500 meters, for instance. Yeah.
So delta y is the height.
Delta y is the change in the position. Okay? If the base of the mountain is 0, then delta y is the height that you're at. Okay? So let's take a look at this table. Now, on the left is the work formula for the work done by gravity. mg delta y. So that's F parallel times delta y. Now, in both of these equations, you must use a negative number for g, as we have been. The work increases with downward delta y. So when you're going downward, delta y is negative, g is negative, so you have negative times negative in this formula on the left. So that's a positive, it increases. On the way, and that should make sense, because on the way down, you get more kinetic energy, you're going faster. Right? So when the work is positive, that means you're speeding up. On the way up, a baseball pop-up, on the way up, it loses speed, so it's losing kinetic energy. That means the work is negative, and that's what you get here. Upward delta y means positive delta y, but you still have minus g, or minus 9.8 meters per second squared. So in this formula on the left, when you go up, the work is negatory. You're losing kinetic energy. Now, GPE is different. It's just the opposite. Look at those formulas. The work is mg delta y. GPE is minus mg delta y. So whatever the work does, GPE is the opposite of that. So GPE decreases as you go downward. So if you're up on a bookshelf, you have a book up on a bookshelf, 2 meters up, and it falls off the bookshelf and moves downward, it loses gravitational potential energy. But what does it acquire more of? Kinetic. Students, 1-for-1 trade-off. As you lose potential energy, you gain kinetic energy. It increases with upward delta y. So think of a bookshelf. A lot of potential energy up on the shelf. If it gets knocked off just before impact, it's got a lot of kinetic energy. Last comment to you today is for when you get to the homework. The homework will be ready a little bit later this afternoon. Using the work formula is really good for figuring out the stopping distance. You can use 1/2 AT squared and so forth, but this one is better. So make a note of that and be ready to roll with homework a little bit later this afternoon. Okay, you're dismissed early. I'll see you. If you want your printout, come on up. Miss Caroline has it. And we'll see you next time.